Welcome to section 4.3. Today we are talking about global maxima and minima. So our first definition, f has a global maximum at a point P if the value f of P is greater than or equal to all other values of the function. And similarly, f has a global minimum at a point P if the function value f of P is less than or equal to all other values of f. Alright, so we're going to jump right into our first example here, where we are to label all points on the graph as either local max or min. Then we're going to go back and label the global max and min. And I just noticed this. I don't know if you guys think this too. This looks a little bit like the Facebook F. Anyways, back to the problem. So first we're going to label all the global max and min. So these are all the little points, and I'm going to use L max or L min for local max and min, and then I'm going to use global max and global min. Alright, so all of these little points here that we're given on our graph, I'll zoom in a little bit. Over here, we're going to start left to right. We have a local max, and then we go down to a local min, back up again to a local max, down again to a local min, and we finish off on a local max. Alright, and now we're supposed to label the global max and min. So there's only going to be one global max and min. Okay? So we have multiple local max and multiple local mins. However, there will only be one global because it's going to be greater than all other points or less than all other points on our graph. So if we take a look here, our local max or our global max looks like it is this point here. If we draw a line through our point, our function doesn't ever get anywhere close to it again, does it? As far as we can tell on this part of the graph. So, this is our global max. Alright. Similarly, down here, if we draw a line through this local min, our function doesn't get anywhere close to that ever again. So this is our global min. Alright, and a singular point can both be a local max and a global max. Okay? So what if, for example, what if our function continued, let's see, and it went down like this? Okay? I guess I'll make it more of a point. So it ends at that point. Then is the global max that we labeled still the global, or the global minimum that we labeled still the global minimum? Well, if we plugged in this endpoint here and we drew a line through our endpoint, it would beat out that global minimum, wouldn't it? Alright. So this is to show that we need to take endpoints into account when we're looking for global max and mins. It's not just the peaks and the valleys anymore. We have to look at the endpoints as well. Okay? So we're going to hit example 2 next, where we want to find all the local maxima and local minima of this function g of x. Alright, so we know that needs to start with finding where the derivative is 0. So we got to take the derivative. It's just a series of power rules, right? So we end up with 3x squared minus 18x minus 48. We need to set that equal to 0. 3x squared minus 18x minus 48. And then we need to solve for x. Alright, so we're going to solve for x. First, we're going to pull out a 3. That'll leave us with x squared minus 6x minus 16. If we divide through by 3, 0 remains 0 over here, and now we just have x squared minus 6x minus 16, which we want to factor into x minus 8 and x plus 2. So that gives us x is equal to 8 and x is equal to negative 2 as our critical points. Right? This is where our derivative is equal to 0. We also care about if our derivative is undefined anywhere. Here we have a polynomial which is defined everywhere, so we don't have to worry about that. Alright, next, to test if either of these critical points are local maxima or minima, I'm going to use the second derivative test. Alright, so that means we need our second derivative, which will be 6x minus 18. And we need to test both of these points. So test the second derivative at 8. That gives us 6 times 8 minus 18, which we don't even need to know the number. We just need to know if it's positive or negative, right? So we know this is going to end up being positive. Alright, which tells us we are concave up, which tells us we have a local minimum at x is equal to 8. Alright, so then we'll test the second derivative at negative 2. So we have 6 times negative 2 minus 18. Again, we know that's going to be negative. Alright, so we have concave down, which says we have a local maximum at x is equal to negative 2. Alright, so we have found local max and local min. Now for part B, we're going to look at this graph of the function. So this is the function from part A. Alright, specifically on an interval, negative 5 to 14. And it asks, are the local max and min that we just found in part A also the global max or min on this interval specifically? So we found we had a local max at x is equal to negative 2 over here. And we had a local min, I'll call this a local max, and a local min at x is equal to positive 8, a local min. Alright, so these are the 2 points we just found. And we are asked, are these the global max and min on this interval? Well, remember, we need to take into account the end points. So we also care about this point here, where x is equal to 14, and this point here, where x is equal to negative 5. Alright? In this case, x is equal to 14, this point over here, gives us our global maximum. Alright? Because it's much higher than the local max we had found before, right? So we've now found our global maximum. And our local minimum that we found at x is equal to negative 8, well, that still beats out this end point over here. So this local min that we found is also the global min. All right? So just for clarity, we would like to list out all of the places that we could possibly find the global maximum and minimum of a function. All right, so first we need to check where the first derivative is equal to 0. All right. Also, where the first derivative is undefined. These are our critical points, right? But in addition to checking our critical points, we must also check the endpoints of an interval. All right, so that would be A and B, or A less than or equal to X less than or equal to B. That's how we would find our endpoints, and we'd check those endpoints. All right, so not only do we have our critical points as options, but we also need to check the endpoints. All right, so example 3. The energy expended by a bird per day is E, and it depends on the time spent foraging for food in T hours. Foraging for a shorter amount of time requires better territory, but then that requires more energy for defense. Find the foraging time that minimizes energy expenditure if energy is given by this function here. All right? So there's a lot of words going on, okay? But all we're doing is looking for the global minimum, the lowest of the low minimums, all right? That is going to give us the smallest amount of energy that the bird has to spend, okay? And we start finding this by finding the critical points. All right, so we need to take the derivative of our energy function. We'll get 0.25, and then negative 2 times 1.7t to the negative 3. All right, which gives us our 0.25 minus 3.4 t to the negative 3. Then we want to set this equal to 0 to find our critical points, right? So we have 0.25 minus 3.4 t to the negative 3. Then we'll go ahead and move this over here, so we get negative 0.25 is equal to negative 3.4. I'm going to go ahead and move this t down to the bottom. All right. I'm going to divide both sides by this negative 3.4. So on the left-hand side, we'll get positive 0.074 is equal to 1 over t cubed. And then I want to multiply both sides by t cubed, so I get 0.074. T cubed is equal to 1. And then go ahead and divide both sides by the 0.074. So I get t cubed is equal to 13.6. So if I go ahead and take the cube root of both sides, we'll get that t is equal to 2.39. All right, so this is a critical point because this is where our derivative is equal to 0. All right. So part B asks what are the endpoints of the interval for which the function e is defined. So we're not given an interval, okay? However, the problem talks about the amount of energy spent by a bird per day, and t is in hours. So if we think about the interval that would make sense is the number of hours that are in a day. Okay, so there's 24 hours in a day. So it would make sense that our interval should be 0 is less than or equal to t is less than or equal to 24, because you'll go from the 0th hour to the 24th hour and then start over again. Alright, so these are our endpoints, 0 and 24. Part C asks us to write down all possible points for a global minimum. Alright, so at the critical points, where t is equal to 2.39, we have another type of critical point. That's where it is undefined, right? And we had dividing by t, so that means we are undefined at t is equal to 0. And then, so these are our critical points, which we found. And then we also need to check at the endpoints. So we also have t is equal to 0 and t is equal to 24. Alright, so part D asks us to test each of the possible points and compare the values to find our true global minimum. Alright, so the original function was e of t is equal to 0.25 times t plus 1.7 over t squared. Okay, so let's go ahead and test t is equal to 2.39. So e of 2.39 is 0.25 times 2.39 plus 1.7 over 2.39 squared. And the calculator tells us that this is 0.89. Okay. And then we would want to test t is equal to 0 next. But if we try to plug in 0, we're going to be dividing by 0, right? We get 0.25 times 0 plus 1.7 over 0 squared. So our original function is also undefined at t is equal to 0. Alright, so that's not a possible option. And then finally, our other endpoint would be t is equal to 24. So if we go ahead and plug this in, we get 0.25 times 24 plus 1.7 over 24 squared. And this gives us 6. Alright, so we are undefined at t is equal to 0. At t is equal to 24, energy level is at 6. But at t is equal to 2.39, energy level is at 0.89. Alright, so the global minimum is at t is equal to 2.39, and t was measured in hours. Alright. Our next example, and our last example, is the quantity of a drug in the bloodstream is t hours after a tablet is swallowed is described in milligrams by this function. Alright, Q of t. Part A asks what quantity of the drug is present at t is equal to 0. Alright, well, at t is equal to 0, we have Q of 0 is 20 times e to the negative 0 minus e to the negative, 2 times 0, also 0. Alright, but negative 0 is not a thing, it's just 0, right? So we have 20 times e to the 0 minus e to the 0, and anything raised to the 0 is 1. So we have 20, 1 minus 1, well that's 0 also. So we end up with 20 times 0, anything times 0 is 0. Alright, so there is no presence of any drugs in the body at time is equal to 0. Alright, so it still needs to be absorbed into the bloodstream. Part B asks us to find the maximum quantity of the drug and at what time the maximum occurs. Alright, so finding a max or min always has to do with taking a derivative. Alright, so let's go ahead and take this derivative. So q of t is this 20 e to the negative t minus e to the negative 2t. So q prime of t, I'm going to go ahead and leave the 20 out front because it's just a constant multiple, and then use exponential rules inside of here. So e to the negative t, that's going to be negative e to the negative t. And then negative e to the negative 2t, our negative 2 is going to come down, make this a positive 2e to the negative 2t. Alright, but then we need to set this equal to 0. 20 negative e to the negative t plus 2e to the negative 2t. Alright, go ahead and divide through by 20, so we get 0 is equal to negative e to the negative t plus 2e. And I'm going to go ahead and write this as negative t squared. Alright, this is just a law of exponents here that I'm using. Alright, so this means I can actually pull out an e to the negative t. Alright, so we have e to the negative t. We have negative 1 plus 2e to the negative t, because we had two of them, right? It was squared. So now we're just left with one of them in there. So we go ahead and divide out by this e to the negative t. We get negative 1 plus 2e to the negative t. So add 1 to both sides, a little bit more space. We get 1 is equal to 2e to the negative t, 1 half e to the negative t, and go ahead and take the natural log of this 1 half is equal to the natural log of e to the negative t. But then we use our natural log property to bring this negative t out and make it a coefficient. Alright, so we have the natural log of 1 half is equal to negative t, because the natural log of e is 1. And go ahead and say negative natural log of 1 half is equal to t. So we get t is equal to 0.69. Alright, so we just found a critical point here. Alright, we don't actually know if this is a max or min yet. So we need to go ahead and use the second derivative test. So, oops, not a g, we need a q. We need the second derivative of q. Alright, well this is going to be 20 times e to the negative t minus 4e to the negative 2t. Alright, this is our second derivative. And so we need to evaluate our second derivative at this point, 0.69. So we get 20 times e to the negative 0.69 minus 4e to the negative 2 times 0.69. This gives us about negative 10 is negative. Alright, so we know that we are concave down. which we know gives us a local max. Alright, so we do know that we have a maximum occurring at 0.69 hours, but we were also asked to find what the max is. So we need to evaluate the original function q of this time where we know a maximum occurs. So this will be 20 times e to the negative 0.69 minus e to the negative 0.69 times 2. Alright, and this gives us 4.999, which we can go ahead and round up to 5, and our units are milligrams. Alright, so the maximum quantity is 5 milligrams, and it occurs at time is equal to 0.69 hours. And finally, part C asks us what happens to the quantity as t goes to infinity. Alright, well, if we just think about this for a moment, we could graph it if we wanted to, and I encourage you to do so. But if we think about this, it is a drug that has been administered once. It's just one pill that was swallowed. And so we know that the quantity is going to peak once it's fully absorbed, and that happens in 0.69 hours. Alright, but then it's slowly going to start tapering off again as it gets used up in the body. And eventually, the drug gets used up entirely, so it gets out of the system. So eventually, the drug will, I'm just going to say, get used up, for lack of better words. And as t goes to infinity, so this is as time goes on for forever, the quantity will go to 0. It's going to level back out at 0 again until the next dose is taken. Alright? Well, that wraps up section 4.3 on global maxima and minima. Please email me with any questions, and don't forget to take the comprehension quiz.